I feel so honored today. I feel so honored.
Oh, does the bell ring?
You just don't, the warm feeling I have that you just honored us with your presence gives me the warm fuzzies.
I'm glad to hear that.
All right, we're going to continue on with imaginary numbers. Okay, yesterday we talked about simplification of imaginary numbers. We are going to talk today about complex numbers and how we can relate these to polar coordinates. Because there's a direct connection between polar coordinates and imaginary numbers and complex numbers. When we deal with a real number or a complex number, these are numbers that have issues. Okay, they have issues. The reason why is they're standing there. They have 1 foot in the real world, and they have 1 foot in the imaginary world. Okay, so they tried to ride that line of both imaginary and real. There's 2 parts to them. You have a real number and you have imaginary numbers. Well, when you look at a complex number, we have 3 plus 4i. This is a complex number. You have a real number part and you have an imaginary number part. Okay, you have real and imaginary. Okay, once again, these are called complex numbers. And complex numbers you can add, subtract, multiply, and divide. If I would add these 2 imaginary numbers together, I would get the value of 8 plus 2i. We could subtract them, but when we're adding and subtracting, you're just combining alike terms. We can multiply them by taking 3 plus 4i times 5 minus 2i. We can multiply them together, but when we multiply them together, what we have to do is we have to go through FOIL. So it's like 2 binomial terms being multiplied together. So multiplying these together, we would have 15 here, plus 20i, minus 6i, and then minus 8i squared. So we'd have 15 plus 14i. Now when we have a minus 8i squared, I squared is a value of what? What's I squared equal to?
8.
What's I squared equal to?
Positive.
Negative 1. I squared is equal to a negative 1. That's equal to a negative 1. So I have negative 8 times negative 1, which would give me a plus 8 there then. So we would have 23 plus 14i. So you can add, subtract, multiply. When you divide, they have division of complex numbers, but really what you're dealing with is simplifying a complex conjugate. And it's not really division, it's just simplification of a radical. What we can do with imaginary numbers is we can also graph them. When we turn this into a graph of imaginary numbers, we are typically dealing with an x-axis and a y-axis horizontally and vertically. But when we go to graph an imaginary number, okay, we have the horizontal axis is your real number part, and your vertical axis is your imaginary number part. So if I'm graphing 3 plus 4i, we would have a value of 3 here and 4 up here. We can plot this point and then draw a line. And that would give us 3 plus 4i. 5 minus 2i, I would go out to 5, down to negative 2. And this would be 5 minus 2I. Basically, what we're doing is we're changing our axes. Changing our axes to real and imaginary rather than an X and a Y. But when we talk about a magnitude, once again, it is the distance. When we talk about magnitude, it is the length of a vector. We talked about that before. But it's also the absolute value or the distance from our origin. What is our distance from our origin? And what this runs it right into is a Pythagorean idea. Okay, he never goes away. Unless he just fades away there. There you go. He is always with us. So if I want to find the magnitude, I can run this right through a Pythagorean equation where we have 3 here, we have 4 here. Even though it's I, we could deal with the square, each component here. And when we find the magnitude of the first one here, my magnitude is the value of 5. My second one, if I want to deal with my magnitude of my second one here, we have the square root of 5 squared plus 2 squared. Once again, it just falls right into Pythagorean ideas again. Or the square root of 29. It's the length from the origin is your magnitude. Once again, they symbolize that by an absolute value. You could double absolute value it, and that would be fine. We have an imaginary, we have a real number. Once again, we can look at our circle here, unit idea of a unit circle. Your x would equal your x would equal r cosine theta, your y would equal your r sine of theta. And then we could write any imaginary number that we want. A z signifies an imaginary number. The value of r, once again, is going to equal the magnitude, which is the square root of x squared plus y squared. Okay, they all still, we have done so many of these things already. We are just giving different definitions and different labels to what we have already done. Okay, so we could talk about imaginary numbers, you know, your Pythagorean idea, your x and y components to vectors, the idea of vectors, and we do the x component, and the y component was r sine of theta, y cosine theta. We can find our components in that way. So all these things have been done for us, or been done already. We're just labeling and applying them to something different. If we would make some substitutions here, x is equal to r cosine theta. Y is equal to r sine theta. So making a substitution, we can say z is equal to r cosine theta plus I r sine of theta. Once again, we are taking the y out and the x out and just replacing with what it's equal to. We can factor out the value of r. R is common in both of these. So we have r cosine theta plus I sine theta. And what they do in the imaginary world and the complex world in regards to notation, they take a look at this right here. They keep our r right here, but then they use c, the imaginary, and I and s, and that gives you CIS theta. Once again, when you see a CIS theta, all it does is it takes us back to r cosine theta plus I r sine of theta. So when you have that CIS notation, it's r cosine plus I sine of theta. So if we take a look and we want to express this in polar coordinates, this here is your polar coordinates. This here is your polar coordinates. I have -1, I'm not sure why I have an I and a J there.
Might have just been a typo.
Yeah, no. I'm going to take the J out, and I'm going to rewrite this as square root of 3 plus a negative I. And I want to write this in polar coordinates. Don't know why I threw vectors in there, but let's take a look at what happens here, or what this looks like. We have our imaginary axis, our real axis, and our imaginary axis. We go out square root of 3 on the real axis. We go down -1 on the imaginary axis. So we have square root of 3 plus a negative I, or minus I. We want to write this in terms of polar coordinates. Well, when we're writing in terms of polar coordinates, what we need to determine is we need to determine a theta here, and we need to be able to determine an R. When we look at the value of R, That's my distance from the pole or from the center. Okay, so we can find our r as the square root of our x squared plus y squared, our Pythagorean idea. So we have the square root of 3 squared plus our -1 squared. Which gives us square root of 3 plus 1 or square root of 4 or 2. This is our R value here. This is our R value here. The next thing we need to find is we need to find what theta is. So we need to find what is this amount of rotation here of theta. Well, if I complete my triangle here, we can find an alpha value by knowing I'm going out square root of 3 and I'm going down 1. So once again, we could go back to what we did with our vectors, Victor, and look at the idea of tangent. The tangent of alpha is equal to, once again, I would suggest losing the negative sign there and just say tangent is 1 over square root of 3. So we can take our inverse tangent of 1 divided by square root of 3 and come down to an alpha value. Our alpha value comes down to what? What do we get, Alex? 30 degrees. So we get alpha is 30 degrees. So if that is alpha, what is our theta rotation then? If this is 30 degrees, what is our theta rotation, Micah? 330 degrees. So we can rewrite our imaginary number as our magnitude, which is a value of 2, cosine of 330 plus our magnitude I sine of 330. Or if I wanted to, 2 cosine 330 plus I sine 330. This is a little bit more acceptable here. So you're looking at this for a solution. Or if you want to, you can write this as 2 CIS 330. Using this notation right here. Basically, it's telling you R cosine, imaginary, sine, 330 degrees. Once again, I would suggest you can use either of these two at the bottom. I would stay away from this, but this is still, it's okay. We can multiply two polar coordinates or imaginary numbers and polar coordinates. When we multiply them, this is equal to the product of both of the magnitudes, R1 times R2. And since we're multiplying, we're going to be adding our angles. Cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. When you're dealing with division, Okay, when you're dividing Z1 divided by Z2. We have R1 divided by R2. Then the cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So when you're dividing your two magnitudes. Your cosine is subtraction of the two angles, top minus bottom, plus I sine of the subtraction of the two angles, once again, top minus bottom. So if we look at two vectors, two polar coordinates, two imaginary numbers, we have Z1 is 6 cosine 60 plus I sine 60 plus 2 cosine 30, I sine 30. And once again, you may see this sometimes as 2 CIS of 30, and this would be 6 CIS 60. Okay, it could be, you can see it in either direction. You can see it as written out, or you can see the CIS is in there. So when multiplying, multiply our magnitudes, add our two angles, I sine, add the two angles. Go ahead and apply. My suggestion is that you physically write out what you're doing here, and then combine them together. Don't say, oh, I just apply that. Just physically write it out, and that will help you remember what you have to do. So you have 6 times 2 cosine 60 plus 30 plus I sine 60 plus 30. So we're left with 12 cosine 90 plus I sine of 90 degrees. Now, what you're able to do with this is if you have your 90s, 180s, 270s, 360s, you can do some additional simplification. If you would take the cosine of 90 degrees, cosine of 90 gives us what? Zero. The sine of 90 degrees gives us 1. So if I can, I can simplify things down, which gives me just, when I distribute this through, 12i. This gives away, and I can multiply 12 times I. So this just gives me 12i. Z1 divided by Z2. once again, when you subtract here, when you subtract your angles, you always go, what is my top value minus what is my bottom value? So I'm going to go theta 1 minus theta 2. So I'm going to subtract them. So we should have 3 cosine of 30 plus I sine of 30. And once again, if I wanted to, I can write this as 3 CIS 30. We can always simplify this down, where if I take a look at a 30-60 right triangle and take it back out of polar coordinates, where we have 30, 60, and a right triangle, 1, 2, square root of 3. The cosine of 30 degrees is square root of 3 over 2 plus I times the sine of 30 degrees, which is 1 over 2. So if I wanted to take this back out of polar coordinates, I can use my angle relationships to give me 3 square root of 3 over 2 plus 3 over 2I. And that takes us out of, this is polar coordinates, back into what we are normally complex AX plus BI, or A plus BI imaginary notation. So you can go from one to the other by using your triangle relationships. Now I wouldn't recommend this unless you have, this is acceptable as a solution here. Okay? If you simplify it down, you can do that, but I'm fine with just leaving it in this form. But I'm just showing you what could be the next level and next step of what you can do with this. You can use your triangle relationships, and I wouldn't recommend dealing with this unless you have 30, 60, 45, or 90, 180s, and simplifying that out a little further. I wouldn't recommend going out any further than that. Questions?